moving on. Right, so I don't know how to draw a picture for this in general. So, so increasing events can look ugly, right? I mean, there's a cube there, thought of as a lattice. So increasing event, I mean, they don't have to look nice at all. Like before, we were talking about the event that's just you contain, you know, the coordinate 1 comes up, yes. Right, so that's a beautiful increasing event, but I mean, most increasing events aren't like that. They have hills and valleys and they look nasty. So there's no nice picture that, at least I can't think of a way to draw this as a picture. However, if we sort of restrict ourselves to the case where all of the events are of the form some set of coordinates all come up 1s, then there's a beautiful picture that we can draw. Right, so now I'm restricting to the case, in order to draw this picture, I'm restricting to the case that all the events are, they're sort of, what do you call it, principal? They have sort of one generator somewhere, and then they're just, the event is that you're above that thing. So I'm not saying the generator is a singleton, right? Maybe this event is the event that coordinates 1, 2, 5, and 17 all came up heads. But anyway, that's the type of thing that the event is. So if all the events look like that, then we can draw, essentially we can draw the situation as a hypergraph. So all the coordinates are letters, and they're the vertices of the hypergraph. And all of those generators for the events are the edges in the hypergraph. Right? And so not shown in the picture is that each vertex has an associated probability on it, right, which corresponds to the particular coin weight for that vertex. So then what's going on? So if the events are all of this form, and we draw this hypergraph, then what is x? X is the thing that counts the maximum number of pairwise disjoint edges that we can find, if we promise that we're only going to use edges that are all 1s after we flip the coins. Right? Or to be technical, it's the matching number in the sub-hypergraph induced by the coins that came up 1. Okay, and what is y? Well, down here I took all these edges and I peeled them apart. Right, so every edge up here is copied down to here, and it has the same letters in it. So obviously, letters with degree greater than 1 appear multiple times in this diagram down here, because they have to be copied into all the edges that they were in up there. But anyway, so that's what I did. I took the edges and I shoved them all apart. So, right, so x is counting the matching number among the edges that came up all 1s in this hypergraph. Y is counting the matching number among the edges that came up all 1s in this hypergraph. It's sort of silly to put it that way, but that's what it's doing. Right? It's just how many of these edges do you get? Where getting an edge means getting all the vertices in the edge. Okay, and I like this this formulation or this restriction because it highlights the tension that's going on in the. So I'll call this the x model and this the y model. Right? This is the thing that supports the random variable x. This is the thing that supports y. So it highlights the tension that's going on in the x model, which is that, so suppose we look at a particular vertex and we observe the coin flip for it and we observe that it came up 1. Well, in this model, that can help a lot of different edges, right? Because a lot of different edges can depend on a single vertex down here, which is not the case down here. But on the other hand, you're only allowed to, at the end of the day, you're only allowed to use one of those edges in your count. your count being x, because x, right, you're not allowed to use two edges that contain, you're not allowed to use two non-disjoint edges, right? So if I'm looking at this coin L here, and I observe that L came up 1, well, great, that helps all three of the edges that contain L, but at the end of the day, I'm only going to be allowed to have at most one of them in a matching whose size x is going to count. Okay, so right, in that spirit, our result, if you want to rephrase it in this way, so if you're looking for a lot of events to happen, forced disjointness is worse than actual disjointness. Right? Forced disjointness being this occurring disjointly condition, actual disjointness being actual disjointness of the edges. Okay, so I'll prove it to you in this restricted case. I think we'll actually have enough time to do it. So I should just remark, the proof for the general case it's basically the same proof, but it's much, much harder to write down. It's one of these things where only the notational difficulties increase, but none of the ideas change, so I think it's perfectly okay to just prove it in this case. Okay, so so at the outset, well, actually, okay, so this is good. So this is similar, okay. I should also remark, right, that this proof is similar to the original proof of BK that was given in the 85 paper. And so the idea, and you'll kind of see this at the end after it happens, but the idea is that we're kind of starting with this hypergraph, and we're going to try to gradually pull apart the edges until we get to something that looks like this hypergraph. Okay, so let's define an operation that you can perform on any hypergraph given a specified vertex, V. So any hypergraph, so the hypergraph has to have probability weights on its vertices. So this is just an operation you can perform on any hypergraph with probability weighted vertices sort of at, quote unquote, a specified vertex V. Okay, so I'm going to do three things. First, here they are. So for each edge containing V in the original hypergraph, add a new vertex, just a new vertex, right? So here, right, so here's V, here are the three edges containing V, and I added new vertices. And I put the vertices in, so one vertex in each of those edges, and those new vertices are in no other edges. Okay, they need to get probabilities assigned to them. So I set the P for those new vertices to be the P for V, the original V. And then I change the P for the original V up to 1. So presumably it was less than 1. I now change it to 1. So that doesn't, of course, mean I change the new ones, right? The new probabilities are the same as what the probability was for the original V, but then I change the probability of the original V to 1. Okay, so main point, and this is really essentially the whole proof. Main point. So for all k, the probability that the original x was at least k is at most the probability that the x in the new hypergraph is at least k. Right? So in some sense, what this is saying is that when we go from here to here, we improve the situation as far as finding a large number of disjointly occurring things. Okay. So so let's prove that. So fix k, and I need to prove the inequality at the top. All right, so flip the coins for all the vertices except for V and its copies. Right, so I know, so sort of all this garbage up here that has nothing to do with the changes I just made, flip the coins for those vertices. Okay, and see how large the largest matching is that you have so far. Right, the largest matching so far, that just means, okay, I'm trying to find just a bunch of disjoint edges of all ones. How many can I find so far without looking at V or any of these new vertices? Okay, call that number S. S is number so far. Okay, so if S is less than or equal to k minus 2, remember I'm looking for k in both cases. If S is at most k minus 2, then neither of those things can happen. Then neither x nor x new can be k. Why? Because once I actually flip the coins for V and the new guys, I can only possibly increase the count by 1. Right? Because the only edges that I could possibly add in all contain V, so I can only add in at most one of them. Whoops. Right, so if my count so far was less than or equal to k minus 2, then I know that there's no question, there's no possibility of either x nor x new being at least k. Okay, similarly, if S is at least k, meaning if by flipping these coins out here, I can already find k pairwise disjoint edges of all ones, then both x and x new are at least k, right? Because once I flip the coins for V and the new vertices, my count certainly can't go down. Right? A largest matching with more vertices is at most the same. Yeah. Okay. Okay, so the rub is what happens when S equals k minus 1. In other words, I flip these coins out here, and the maximum size matching that I can find so far out here has size exactly k minus 1. Okay, then I have to sort of think about what happens. Okay, so 2 subcases. So first of all, in order for either x or x new to increase, there has to be an edge that's eligible to be added. Right? And an edge that's eligible to be added is an edge like this. So there has to be an edge of the form E union V. So obviously V has to be an element of an edge that's going to be added, because the only edges we can add contain V. So the edge has to be the form E union V, where E, so all the other vertices in the edge have to have come up once. We already know that. And E has to be disjoint from every edge of some largest matching so far. That's the only way we could add it in, right? Because we're not allowed to add anything that overlaps with anything we already have. Right, so just to say that again, so suppose S is k minus 1, we can find the largest matching of size exactly k minus 1 out here. In order to have any hope of increasing the size of our maximum collection, we have to have an edge that's eligible to be added into a largest collection. Right, so what is an edge that's eligible to be added into a largest collection? It's an edge, all of whose other vertices have already come up with coin flips of 1. And that edge has to be disjoint from every edge that's in an already largest collection. Right. So if there's no edge like that, then neither x nor x new can possibly increase. Right? Because we just said there has to be an edge like that in order to be able to add something in. Okay. So here's the interesting case. What if S is exactly k minus 1? So we have exactly, the matching is size exactly k minus 1 so far. And there is an edge like that. There is an edge that we could possibly add in if the coin flip for V comes up heads. Well, okay, then what happens is on this line here. Then the probability that X increases is exactly PV. Right? We just flip the coin for V, and if it comes up heads, then we increase the size of the maximum thing. And what's the probability that X new increases? Well, the thing about x new is that it gets so there might be several edges like that. There might be several candidate edges, right, where a candidate edge is one of the ones that could have possibly increased the size of the maximum collection. Right? And for each one, x new gets an independent try, all at probability PV. Right? So we have that inequality there. Right? The probability that x increases from k minus 1 to k is at most the probability that x new increases from k minus 1 to k, because each of the candidate edges in the x new hypergraph gets an independent attempt. Okay, so that proves the main point, right? Because I partitioned the space into 4 subparts, and I proved the inequality on each of the 4 subparts.
Can I make a comment
Yes.
before the time runs out?
Yes.
You were asking if this stuff was known beforehand.
Yes.
It reminds me a lot of work in information theory.
Okay.
There's a book by Chiza, Emery Chiza, I recommend that you look at. You think of maybe you're going to think of the x's as the inputs to a channel, and the y's as the outputs, or something. It would be worth looking into that.
Yeah, that's definitely not something I had looked at all. Let me get the information after the talk. Okay, so right, so I have the main point. So now we're basically done. So what do? So I start with my original hypergraph, and I just perform the operation on each of the original vertices in succession. Right? So I get this string of stochastic domination inequalities. Okay, and so what's the punchline? So the last one, once I've done the last one, so I've sort of neutered all the original vertices and replaced them with these new guys. So in the last hypergraph, the edges actually occur independently. Because, well, why? It's right here. So all the original vertices, their probabilities have been changed to 1. So the original vertices essentially play no role in determining whether or not the edges show up, because all those vertices automatically show up. And so the only vertices that actually have any probability are the ones we added. And all the vertices we added had degree exactly 1. So every vertex we added only affects one edge. So those are the only vertices in play. So the edges come up independently in this last one over here. And so, oh no, my please clean filter is obstructing a line. And so this last one is just strictly less than or equal to y. Right? Because y is the number that show up without worrying about this disjointness. X has this last one. The edges' probabilities are the same, but they bump into each other at the neutered vertices. Right? So there we go. Okay, great, thank you.